Introduction to plasma nitriding content. Introduction, equipment, definition, case structure, material for nitriding, measurement of case depth, identification of materials, etching, experimental conclusions for varying parameters, experimental conclusions for RE nitriding, objective, enhance understanding in the process of nitriding. Impart ability to differentiate between plasma nitriding and plasma nitrocarburizing. Introduction to the equipment for plasma nitriding. Standardizing and optimizing handling skills for the treatment process. Understanding analytical skills in testing of the results. Impart ability to identify material. Reinforcing understanding of the effects of varying process parameters. Introduction. Advantages of case hardening. Less distortion compared to through hardening. Fatigue properties can be controlled and frequently improved. Inexpensive steel made wear-resisting, similar to expensive alloyed steel. Steel, which cannot be hardened to a high degree, can have their surface hardened through alteration of the surface composition. Combination of case and core properties attainable. Minimizes scaling and decarburization, desirable in producing machined parts. Applicable to large parts, which may crack using conventional heating. Selected area can be hardened at high surface hardness, improve resistance to wear and galling, improve fatigue life, improve corrosion. Resistance, stainless steel is an exception. Introduction. Type of case hardening methods: carburizing, carbonitriding, nitriding, gas nitriding, liquid nitriding, plasma nitriding, nitocarburizing, boriding, sulfurizing, sulfonitrocarburizing, oxidation, induction, flame, magnetic, shell, electron beam, laser, plating, sprayed metal coating. Introduction. Advantages of plasma nitriding. Ability to automate the system, which gives good reproducibility of results. Shorter cycle time, no environmental hazard. Improved control of case depth. Ability to select the compound layer type to suit the required usage. Good friction, wear and fatigue properties. High hardness of the treated surface. Flexibility to nitride stainless steels, titanium alloys. Possibility to lower nitriding temperature and to limit distortion. Introduction. Plasma, ionized gas, is the fourth material stage. It is a very reactive medium which contains ions, very energetic neutral particles, as a result of dissociation, separation of gas molecules in an electric field. The glow layer surrounding the job part is formed by these positive ions. Plasma nitriding utilizes plasma discharge physics to diffuse nitrogen into the surface of a ferrous alloy. Plasma nitriding can be further branched out into plasma nitrocarburizing when carbon is diffused together with nitrogen into the surface. Introduction. Process parameters. Temperature 400 to 580 degrees Celsius. Pressure 0.5 to 7 millibars. Gas composition: ammonia, nitrogen, methane, hydrogen, and argon. Time. Additional process parameters: voltage, current intensity, pulse duration, pulse pause frequency and duration. Equipment's Rubig plasma. Assisted CVD/nitriding/hard coating furnace. Rubig plasma nitriding furnace. 65 vacuum lawn. Nitriding furnace. Definition. Molecular nitrogen is first broken into atomic nitrogen through direct plasma dissociation. N2 plus En plus N plus E. Atomic nitrogen is then further converted into nitrogen ion through plasma ionization. N plus plus 2. N plus E bar. The nitrogen ion, En plus, will then diffuse into the metal surface as finely dispersed nitrides, imparting high hardness to the surface. Case structure. There are three types of nitriding layer that could be formed during plasma nitriding layer formation 1. No compound layer formation. 2. Gamma prime white layer formation. 3. Epsilon prime E white. Layer, case structure formation of no compound layer 1 to 5%, N2 99 to 95%. Balance at carrier gas temperature 530 to 550 degrees Celsius. Time less than 6 hours. Formation of monophased white layer, gamma prime Y, Fen. Gas composition equal to 15 to 30% N2, 85 to 70% balance carrier gas temperature, 500 to 570 degrees Celsius. Time 1 hour onwards. Formation of monophased white layer, epsilon prime, P2,3CH. Gas composition approximately 72% nitrogen, 1 to 3% CH4, 27 to 25% balance carrier gas temperature, 570 degrees Celsius. Time 30 minutes to 6 hours. Material for nitriding: steel with low affinity with nitrogen, carbon steel, low alloy, steel with high affinity with nitrogen, medium alloy steel, tool steel, high-speed steel, stainless steel. Chemical symbol for elements: Fe:, iron, N:, nitrogen, Mo:, molybdenum, H:, hydrogen, Mn:, manganese, Cr:, chromium, Si:, silicon V, vanadium, Al, aluminum, T, titanium. General practice before nitriding: all parts must be degraded to get quality results for their metallographic structure. Gloves must be worn to handle the parts. A finish between 15 and 30 RMS is recommended for optimum plasma nitriding. Jobs that have thin wall sections will result in brittleness after treatment. Job parts with thin-walled sections are not recommended for nitriding treatment unless a shallow case depth is specified. General practice: the overall appearance of a nitrided product is chalky gray color. In some cases, parts may be produced with a black surface. Understand the parts to be treated and define the place not to be nitrided. Space out the parts treated to enable the passage of the plasma, at least 15 millimeters depending on the different furnace. Understand how to protect the parts that are not to be treated. Jobs should always be kept under watch through the potholes, and pressure should be adjusted accordingly. Case depths. Effective case depth, ECD. ECD is the distance from the surface when the reading is 150 HV higher than the core hardness. Total case depth. Total case depth is the perpendicular distance from the surface of a hardened case to the point at which differences in chemical and physical properties between the case and the core can be distinguished. Measurement of case depth. Hardness. Transverse method. The case depth is measured utilizing a Vickers hardness tester. An indentation is made using a load of 100 or 200 grams force at the interval of 0.1 millimeters from the surface until there are no changes in the size of the indentation. Microscopic method. From the sample, cut a test piece perpendicular to the surface and mount it. Polish and etch the test piece. Measure the darkened zone for the total case depth. This method is only recommended when the hardness transverse method fails. It can only measure the total case depth. Etching material. Tool steel, alloy steel oil, hardened steel, carbon steel, stainless steel chemical used mix 4 to 10% HNO3 in ethanol. Mix 50% HCI, hydrochloric acid, 25% HNO3, nitric acid, and 25% of distilled water. Duration about 10 to 20 C or until the sample becomes a silvery color. Etch for about 40 to 60 seconds. Some example of microstructure after etching. Experimental conclusion for varying temperature and time. AISI 630. Increase in temperature will result in an increase in the ECD formed. In addition, increasing temperature will also lead to a decrease in the surface hardness. Generally, an increase in the duration of treatment time will result in a decrease in surface hardness. It also carries the effect of increasing the ECD formed. Experimental conclusion for varying pressure, AISI 4340. Increase in pressure will result in an increase in surface. However, pressure is more often used to control the thickness of the plasma during treatment. Experimental conclusion for varying parameters, CA 6 mm stainless steel. Increase in nitrogen percentage will result in the following: increase in surface hardness, increase in ECD improvements on hardness profile. Introduction of carbon will decrease the brittleness of the nitrided surface plasma. Nitrocarburizing would result in a tougher surface compared to L plasma nitriding.